The figure shows arrangements of springs. They have stiffness K1 and K2 as marked. Which of the following arrangements offers a stiffness 2K1 K2 by K1 plus 2K2? It is a 1987 GATE 1 mark question, and you can see the different arrangements are given as options. Okay, we must know stiffness is given as load by deflection. Newton per meter is the unit of stiffness. Okay, generally similar to bars in parallel and bars in series, the springs will also be having the same conditions. That is, for parallel connection of springs, the deflection will be constant and the total load acting on the parallel connection is equal to sum of the loads. Similarly, for springs in series, the load is constant and the deflection is the sum of deflections on each spring. Okay, so using these conditions, we can write it as PT is equal to, that is total load on the spring connection, that is a parallel spring connection, is P1 plus P2, the total springs. That is, for example, if there are two springs, you can write it as PT is equal to P1 plus P2. So KT, from PT you can find the total stiffness. Total stiffness is given as a load by deflection. So PT is equal to deflection into K. So deflection into KT. Since deflection is constant, you'll be cancelling it out and you'll be getting KT is equal to K1 plus K2. Similarly, for series connection also, deflection is the sum of deflection. So you have to write del T is equal to del 1 plus del 2. In such a case, you will be getting, instead of del 1, you will be writing P by K. So you will be getting 1 by KT is equal to 1 by K1 plus 1 by K2 since load is constant in all the springs. So now you have understood for parallel connection, for series connection, how to find the total stiffness. Okay, here they have given the total stiffness of a setup. This fraction can be written as 1 by KT, that is total stiffness of the setup of the arrangement, is equal to 1 by K1 plus 1 by 2K2. These two fractions sum up to be 2K1 K2 by K1 plus 2K2. So you can see that a spring with stiffness K1 and a spring with stiffness 2K2 arranged in series connection will give such a stiffness. So it is clear that K1 and 2K2 are in series connection. Okay, 2K2 refers to K2 plus K2, which means two springs of K2 stiffness are connected parallelly. So K2, K2 parallel, and this parallel connection is in series to a K1, which is option D. Okay, this is one way of deciphering the given stiffness and finding the arrangement. Another way is to calculate the total stiffness in all the cases and comparing that with the given question and finding the answer. It will be time taking. So it is better to come from the question itself. That is 2K1 K2 by K1 plus 2K2. Just by seeing itself, you can say that it is the sum of two fractions. That is reciprocal of the sum of two fractions, 1 by K1 plus 1 by 2K2. So just by finding 1 by K1 plus 1 by 2K2, you can say that both are in a series connection, K1 and 2K2. Since it is 2K2, so two parallel connection, two springs are in parallel connection, K2, K2, and then in series K1. So K2, K2 in parallel, and then in series K1. So D is the right answer. A helical compression spring made of a wire of circular cross-section is subjected to a compressive load. The maximum shear stress induced in the cross-section of the wire is 24 megapascal. For the same compressive load, if both the wire diameter and the mean coil diameter are doubled, the maximum shear stress induced in the cross-section of the wire is. Here you can see that helical compression spring is subjected to compression. So the spring is subjected to compression. The maximum shear stress is on the wire, the particular wire, not on the whole spring. The particular wire is 24 megapascal. They are saying that for the same compressive load, if wire diameter and mean coil diameter, what are wire diameter and mean coil diameter? Wire diameter is the diameter of the wire which is used to form the spring. That particular wire, small thin wires, dia is referred to as wire diameter, and the mean coil diameter is the mean of the internal and external dia of the spring. Di plus d naught divided by 2, you will be getting mean coil diameter, which is denoted by capital D. Okay, they are doubling the diameters, that is wire diameter and mean coil diameter, and they are requesting the maximum shear stress in the cross section of the wire. Okay, first, due to this compressive load, we must know the load acting on the cross section of the wire. Due to this load, we need to find the cross sectional load acting on this cross section. So how to find that? Instead of this load, we are replacing this load here by an equal and opposite load. So both will be cancelling out. So there will be null effect due to this. But to find the effect here, we are doing this. So W and W will be forming a twist, that is a torque, and W will be acting downwards. So here I have shown the cross section separately. Here you can see a W shear force and a W d by 2 torque, a twisting couple. Okay, now you can understand that due to compressive load, whole spring experiences compression while wire experiences direct shear and twisting. So finding the direct shear stress and the torsional shear stress, we have learned those concepts regarding direct shear stress and torsional shear stress in the previous cases. So you will be getting the direct shear stress as W divided by pi by 4 t squared. Generally average direct shear stress is taken. Okay, and plus the torsional shear stress is 16t by pi d cube. So instead of t you will be substituting WD by 2. So you will be getting a particular equation, which upon simplifying you will be getting AWC by pi d squared into KW, where C is referred to as D by D, that is mean coil dia divided by diameter of wire, which is spring index. Generally spring index value ranges from 4 to 12. Okay, reciprocal of spring index is called as spring compliance, remember that, and KW is referred to as Wahl's factor. You may request the derivation of this, but that is not important. So I have given the direct formula. It is derived in such a way by finding the direct shear and torsional shear stress. Okay, KW Wahl's factor is given as 4 into C, that is spring index, minus 1 divided by 4 into spring index minus 4. This KW accounts for effect of direct shear stress, because here we are putting a common value and we are adding the direct shear stress effect in KW. So the effect of direct shear stress and stress concentration due to curvature, it is curved, it is not a straight beam, so it is curved. So there will be an effect due to curvature also, that is also included in this KW. If you are trying to neglect this stress concentration due to curvature and you are considering just direct shear stress concept, it will be AWC by pi d squared into KSH, where KSH refers to shear stress correction factor. Instead of KSH, here you can see that KW is 4C minus 1 by 4C minus 4. For KSH, it can be written as C plus 0.5 divided by C. That is, it also can be written as 1 plus 0.5 by C. If it is C plus 0.5 by C, it is said as C plus 0.5 whole divided by C. But if it is said as 1 plus 0.5 by C, it is said as 1 plus 0.5 by C. Okay, remember that. This is not required. That KSH is not required. So I have given KW directly. This is the total. That is, we are considering all the effects and we are finding the maximum shear stress. Tau max is directly proportional to D by D cube. How did I say that? You can see that here it is C. Instead of C, you can substitute capital D by small d, where capital D is mean coil diameter and D is wire diameter. So you'll be getting D by D cube, 8W and pi. Since load is constant, we know that 8 and pi are constant. So tau max is directly proportional to capital D by small d cube. So tau max 1 by tau max 2 is equal to D by D cube, while the diameter is increased. So 2D by 2D whole cube, you'll be getting, as a whole, you'll be getting 2 by 8. So 1 by 4, it will be increasing by 4 times. Tau max 1 is equal to 4 times of tau max 2. So 4 into 6, you will be getting 24. So 6 megapascal is the right answer. It is a detailed concept. Remember, direct shear stress and torsional shear stress and the stress concentration due to curvature and all these things are considered, and tau max is derived, which is given as AWC by pi d squared, where C is the spring index and KW is the Wahl's factor. Remember this, Sometimes if stress concentration due to curvature is need to be neglected, you can write it as AWC by pi d square. The same, but instead of KW, it will be KSH, which is given as C plus 0.5 whole divided by C. If you simplify it, you will be getting 1 plus 0.5 by C. That is I have stated earlier. Okay. But generally we will be using this formula only. They will never neglect this stress concentration due to curvature. If they neglect that, we should not consider Walsh factor. We should consider shear stress correction factor, that is KSH, which I have said earlier. Okay, this is the actual question and the answer is 6 megapascal. The deflection of a spring with 20 active turns under a load of 1000 Newton is 10 mm. The spring is made into two pieces, each of 10 active coils, and placed in parallel under the same load. 10 active coils means the previous spring is split into two and they are placed parallelly. And they have asked the deflection of this parallel system. It is a 1995 gate 2-mark question and you can see the different options of deflection values. Okay, first deflection is derived using Castigliano's theorem. That is, the strain energy of the whole spring is determined and it is differentiated with respect to the load. You will be getting the deflection, which is equal to AW capital D cube N divided by GD power 4, where W is the load, capital D is the mean coil diameter, and N is the number of active turns of the coil divided by G is the shear modulus or modulus of rigidity, and small d is the wear dia. So we know that capital D by small d is spring index. So you can write it as AW C cube N by GD. Okay, we know that stiffness is load by deflection. So W by this AWD cube N divided by GD power 4, you will be getting the stiffness to be GD by HC cube N. So you can see that the stiffness is inversely proportional to the number of active turns of coil. So you can see that for 20 active turns, the stiffness is 1000 divided by 10. So it is 100 Newton per mm. So the Kf dash of one spring, that is after it is split into two pieces, that is N is reduced by 2. So if it is reduced by 2, the K will be increased by 2. That is 2 times. So it will be 200 Newton per mm. And they are placing it in parallel. As we have discussed earlier, if two springs are in parallel, the total stiffness, that is parallel Kf stiffness, is equal to sum of the stiffness, which is 200 plus 200, 400 Newton per mm. So we know that the stiffness is 400 Newton per mm, while the load remains the same. They have said that the load is same. So 1000 divided by 400, you will be getting 2.5 mm as the answer. The spring constant of a helical compression spring does not depend on, they have highlighted does not in the question itself. Okay, it is a 2016 set 1 gate 1 mark question. And they have asked spring constant. What is spring constant? Stiffness is referred to as spring constant sometimes, and sometimes it is referred to as spring rate also. So spring rate, spring constant, and spring stiffness all are one and the same. And they have given different parameters. And they are asking upon which it does not depend on. So we must know on which it depends on first. So stiffness is equal to GD power 4 by 8D cube N. So K depends on, that is stiffness depends on shear modulus G, diameter of wire D, and mean coil diameter capital D, and number of active turns of the coil N. So coil diameter will be excluded because it depends on coil diameter and number of active turns and wire diameter. Don't mistake shear modulus to be the material strength. Generally, shear modulus is the modulus of rigidity. It does not refer to the strength of that material. So, material strength, generally UTS, ultimate tensile strength, or yield strength, these are referred to as material strength. This material strength is not indicated here. So, K does not depend on material strength. A weighing machine consists of a 2 kg pan resting on a spring. In this condition, with the pan resting on the spring, the length of the spring is 200 mm. When a mass of 20 kg is placed on the pan, the length of the spring becomes 100 mm. For the spring, the undeformed length L, that is actual length, that is free length of the spring, and the spring constant, as I have discussed earlier, spring constant is stiffness. they have asked. It is a 2005 2-mark question and they have given different values. We know that stiffness is given as load by deflection, W by deflection. We know the load they have given us 2 kg first and then it is 20 kg plus 2 kg. And they have given the length of the spring after the load is being applied. So we need to find the deflection, which is original length or undeformed length or free length minus final deformed length. Here the original length is not known, that is to be determined. So let us imagine it to be L, capital L. So it is L minus 200 and it is L minus 100. First, the load is 2 kilogram. So 2 into G, acceleration due to gravity. 2 kilogram into G divided by L minus the length of the spring. That is, the deformed length is 200 mm. So it is L minus 200. You will be getting the deflection. 2G divided by L minus 200 is equal to K. And since it is the same spring, so the stiffness will not be varying. So K is equal to, along that pan, we are placing a 20 kg on that pan. So the load will be 22 kg into G, that is acceleration due to gravity, divided by the deflection, which is L minus the deformed length is 100 mm. So L minus 100. So equating these two, you will be getting L and K. Very easy to find. It is a very simpler question. Just you must remember load by deflection, and deflection is original length minus final deformed length. 200 100 are final deformed lengths and we know the loading. So it is easier to find K and L. A compression spring is made of music wire of 2 mm diameter having a shear strength and shear modulus of 800 megapascal and 80 gigapascal respectively. The mean coil diameter is 20 mm, free length is 40 mm and the number of active coils is 10. If the mean coil diameter is reduced to 10 mm, the stiffness of the spring is approximately. They have asked the mean coil diameter. If reduced to 10 mm, then the stiffness will be. They have asked the stiffness if the mean coil diameter is reduced to 10 mm, which means it is decreased by 2 times. So we must know the relation between stiffness and the mean coil diameter. We know that stiffness is equal to GD power 4 by 8D cube N. From here, it is obvious that stiffness is inversely proportional to cube of the mean coil diameter. So if the mean coil diameter is reduced by 2 times, the stiffness will be increased by 2 power 3 times. So it will be increased by 8 times. If the wire diameter of a compressive helical spring is increased by 2%, the change in spring stiffness in percentage is correct to 2 decimal places. Here we must know the relation between the wire diameter and spring stiffness. They have asked the change in percentage. It is a 2018 set 1 mark question. We know that K is equal to, that is spring stiffness is equal to GD power 4 by 8D cube N. Here small d is the wire diameter. So K is directly proportional to D power 4, which is wire diameter power 4. So you can write it as K2 by K1. K2 refers to the final changed spring. That is the stiffness of a spring whose wire diameter is increased by 2%. So it will be K2 by K1 is equal to D2 power 4 by D1 power 4. D2 is given as 1.02 D1. Since it is increased by 2%, it can be written as 1.02 times of D1. So we will be getting K2 by K1 value just by substituting D2 is equal to 1.02 D1. So using this ratio, we need to find the percentage change in K, which is given as K2 minus K1 by K1. We know that for a change in a particular value, the changed value minus original value divided by the original value into 100, you will be getting the percentage. So here we have done the same. K2 minus K1 divided by K1 into 100%. Using this ratio, you will be getting a value. Instead of K2, you have to substitute that value into K1 minus K1 by K1. You will be getting a particular value into 100. You will be getting 8.243%.